All right, so you are going to notice that there are still a few remaining p-values that are well above our zero point 0.1 alpha range. So what we're going to be doing is we're going to be repeating this entire process until all of our variables have a p-value that's below 0 0.1. So the next step we're going to take is we're going to look at the highest p-value out of all of these, which is the 0.79, which is our cloud coverage, and then we're going to remove that from this entire set. So I'm going to go ahead and go up to row 57 over here with my entire table of data, and then paste it down here to row 83, let's say. And then I'm going to go ahead and cut, Control X, and then Control V over my cloud coverage. And now we've reduced the number of variables. Then I'm going to go up to my ribbon, go to Data, select Data Analysis, Regression, and then I'm going to select my new input Y range, which is my directivity down here, and then my new input X range, which includes my variables excluding cloud coverage. Everything else remains the same, and then output range, I'm going to place it here on row 83, and then select OK. Now make sure to save your work along the way, so I'm going to go ahead and press Control S. Great. All right, so let's take a look at these numbers. So what we see here are quite a few new p-values that are well below our 0.1, and that's exactly what we want to see. There's still a few p-values that are above my 0.1, like minimum temperature, for example, which is currently my highest p-value. So what are we going to do next? You guessed it, we're going to repeat this entire regression model. We're going to duplicate this data table from row 83, paste it down to row 108, let's say, and then we're going to go ahead and remove minimum temperature. So I'm going to cut all of my values from maximum temperature to pressure, and then paste it over my minimum temperature. Then go back up to my ribbon, select Data Analysis, select Regression, and then press OK. Then the new input Y range is going to be my new directivity down on row 108. My input X range is going to be my new set of variables excluding minimum temperature. And then my output range is going to be here parallel on 108. And then I'm going to press OK, and then we get a new set. So let's take a look at these numbers. All right, so what you're going to start to notice is most of our p-values are now well below 0.1, and that's absolutely great. The only one that remains above 0.1 is our dew point, and that's at 0.2. And before we eliminate that from our variable set, I want to go back to our R-squared value here, just to explain a little bit about what's happening. So as I had mentioned before, our R-squared value is expected to either stay the same or decrease over time. Now, at the very beginning, we had a p-value of a little over 0.96, and now we're at 0.928. So our R-squared is dropping. However, our overall model is getting stronger as our p-values are reducing in value. And that's a really great trend to see. The other number to note here is our adjusted R-squared. You may be saying, well, what's the difference between these two? Well, frankly, most of the time, we're only going to be focused on our R-squared value. If we have a good R-squared, we don't really need to pay attention to this adjusted R-squared. However, you'll notice that our adjusted R-squared at the very beginning had a value of 0.33, whereas our R-squared was at 0.96. Our new adjusted R-squared is now at 0.86, and our R-squared is at 0.92. The way adjusted R-squared really works is it says that if we have a lot of variables in our model, we may want to adjust our R-squared downwards, because the more variables we have to rely on, the less effective our model is at predicting the outcome, because that means we have to rely on a lot more variables. That gives us a lot more unknowns. So our adjusted R-squared is not really important, but I just wanted to give a little aside to give a little interesting fact along the way. So as we had mentioned, there was one p-value that remained here that was above our 0.1. So I'm going to go ahead and repeat this entire process. I'm going to duplicate, Control C. I'm going to paste it at row 133, And I'm going to remove dew point by pasting my pressure over it, and then go back up to data analysis. I'm going to go ahead and press OK for my regression. My input Y range is going to be this new directivity. And as you guessed it, my new input X range is going to be my new set of variables excluding my dew point. And finally, my output range is also going to be parallel to this 133 here. And then I'm going to press OK. All right, so this is what gets me excited. Let's take a look at all these p-values. All of these p-values are well below 0.1. The highest p-value here we have is maximum temperature, which has a p-value of 0.03. And that is well within our significance range. So at the moment, we appear to have a model that will help us predict our directivity within about 90%. So this is really great to see. This is where we want to be once we've finished up our stepwise regression model. The next thing we're going to start doing is we're going to put together our entire formula, and we're going to start using this coefficients column here to start developing that formula to help predict our directivity. All right, so in order to start using these coefficients, what we're going to do is we're going to develop this model. And what coefficients allow us to do is they're going to be used as our multiplying factors. So whenever we get a forecast of our weather, like for example, our forecasted wind speed or precipitation intensity, we're going to plug that into our model and multiply it by their corresponding values. And then that will help us predict our Y value, which is our directivity. So in order to visualize this, I'm going to go ahead and paste a formula and graph over here. So this is essentially what we're going for. We're going for our Y, which is our directivity, equals mx. So our m value is going to be our coefficient, and x is going to be whatever forecasted value that we get for our weather, plus b. And b is going to be our intercept. In this case, it's negative 57,759. And our intercept, all that tells us is where our line on our graph really begins. So if we get a value of 0 for maximum temperature, then we're going to have our line graph start all the way down here at negative 57,759. Now, what we're doing here with this model is we're adding together a variety of different variables. So it's not just mx plus b, it's going to be mx1, which is our maximum temperature, plus mx2, which is our wind speed, plus mx3, which is our precipitation intensity, and then mx4, which is our pressure, plus b, which is our intercept of negative 57,759. And that will give us our directivity value. All right, so hopefully that was a useful explanation, but in reality and in practice, this is a lot easier than it sounds. We now have everything that we need in order to put together our formula that looks very similar to this. We have all of our coefficients. So why don't we go ahead and do a real scenario analysis over here. So let's go ahead and delete our formula, our graph, and then let's go ahead and take all of these values, our coefficients and our variable names, Control C, and then paste it down here by doing right click and transpose. And that effectively rotates all of these values. I'm going to go ahead and remove some of these borders that are appearing here, and then create a little bottom border over here. Then I'm going to go ahead and name this m values. That's what we saw in the formula beforehand. This isn't very important. All we just need to know and make sure that we remember is that these values are going to be our multipliers, and then our x values are going to be all of our forecasted values from whatever weather resource that we're gathering from. Now, in order to get our output, we're going to go ahead and name this output forecasted directivity, nice and creative. Merge all of this together to make it look clean and organized. Merge that as well. And then let's go ahead and do a real scenario. So let's say that on any one given day, we have a maximum temperature of 88.32, wind speed of 2.24, precipitation of 0.008, and then this pressure of 1016. In fact, let's go ahead and just paste all of these values in here. This is just an example, but hopefully what we should get is roughly this directivity of around 15. There is some error involved, and I'll explain just about how much error there's going to be very shortly. So let's go ahead and put our model together here. So what we know is we have our intercept, which is our B value, and it's not being multiplied by anything. So we're going to do equals our intercept value plus, and then we're going to start working around with parentheses, open up a parenthesis, take my maximum temperature, multiply my M value by my X, and then I'm going to do this whole parentheses over again for my wind speed. And then I'm going to keep adding all of these values together times my precipitation. And then I'm going to open my parentheses, take my pressure, and then take that value, close parentheses. And then hopefully when I press enter, I'm going to get a number that's pretty close to 50. So let me go ahead and do just that. So let's go ahead and round this up. We're going to remove some of these decimal points. So what we're seeing now is that our forecasted directivity is 15.79. So you may say that my forecasted directivity here is 15.79, but I have a directivity of 15 over here. So why don't I just use this directivity if I get a temperature around here and my wind speed is around here? Well, the fact is that most of the time these numbers aren't going to be exactly the same the next time around. And as you'll notice, when I got a directivity of 14, I had a different maximum temperature at 88.94, a wind speed at 2.86. And so overall, I'm getting different values, but I'm still getting a directivity that's very similar. So that's the power of using this formula. So the next time when you forecast your temperature for the upcoming weekend, all you'll have to do is just plug in all of these numbers, maximum temperature, wind speed, my forecasted temperature, wind speed, precipitation, plug it into the model, and then you'll get a forecasted directivity, which should be within a certain amount of error of your actual directivity that weekend. So how do we know how close we got to our actual directivity? Well, that's where a standard error number comes from. Our standard error says within 1.5 units from 15.79, we can guess that our directivity is going to be in this range over here. So our range really is between, let's say, 15.79 minus 1.5, and then 15.79 plus 1.5. So our expected range within 90% accuracy will be between 14.24 and 17.3. You may say, well, you can't get a decimal point of directivity, but that's not what matters. What matters is we can expect to see dir between around 14 and 17 directivity units happening within that day. And that's extremely powerful because now we can go into our next weekend knowing, or at least expecting, the relative amount of dir we're going to be seeing. So if we were to put our model in with a different set of temperature and wind speed numbers, and we get a forecasted directivity of, let's say, 2, you may say, well, actually, maybe Saturday is not the right day to go out on. Let me go ahead and take a look at my forecasted weather variables for Sunday. And let's say Sunday, I get a forecasted directivity of 15, which is much higher than my 2. I may instead decide to go out on Sunday rather than Saturday. And that's the power behind using regression analysis. Now for the last step, what I'm going to do is, just for fun, I'm going to map out all of these expected values using just these X variables we have here, and then compare our numbers to our actual directivity on those specific days. And if we get two graphs or two line graphs that are relatively similar, then we can see how powerful this model really is. So let me go ahead and delete this set of values of my range here. And you know what? I don't need this merged over here. This keeps everything a lot more simple. Now let me go ahead and paste all of these values down here. And then, as you may recall before, what we did was we did this whole dollar value. So we're getting this awfully large number over here, and the reason being is we've moved all of these values down one row. So let me go ahead and go back up here and make sure I've locked in all of my numbers. So I've locked in my intercept, my wind speed, my maximum temperature, precipitation, and I'm keeping the values open that are all of these so-called forecasted weather values over here. And then I'm going to go ahead and just double click and drag down. So now we have our entire forecasted deer activity using just these weather variables. Now let's go ahead and compare. So I'm going to go ahead and copy all of this, paste it in here using right click, and then just paste the values. I'm going to remove some of these decimal points. I'm going to take my actual deer activity. I'll use the label as well. Let me label this as forecast deer activity. Great. And then let's go ahead and graph it. Oh, and in this case, what you do see is we do have a duplicate over here, and this was in the wrong spot. And because we took all the values from 83.55 down, so we're going to move all of this up here, this down here. There we go. That number looked awfully large. So I do recommend doing a little bit of eyeball analysis every now and then again, just to make sure that all of the numbers look right. I'm going to go ahead and do insert line graph. And then let's do this. Let's title this forecasted and actual deer activity. And look at that. Look how close these lines are to each other. They're never going to be exactly the same, except for in this case, they look really close to each other. But the forecasted deer activity here was 4.93, and the actual deer activity was, I guess, 5. Is that correct? Yes, it is. So this is the power behind this model. If we didn't have any of this deer activity information, the actual deer activity information, and all we had was our forecasted weather information, we'd be able to plug in all of these numbers and we get numbers very close to our actual deer activity. And that's exactly what we want to see from our regression exercise. So let's just go ahead and save this doing Control S. And then I'm going to cover one last little piece of this and then go ahead and call it a day. So one thing to be reminded of is in order to construct this model, we used our X variables or our weather variables within a certain range. So we had a maximum temperature between a range of just around 83 and 94. Our wind speed was also within a certain range. And so whenever we start looking our forecast for the upcoming week, we do want to make sure that our temperature, our wind speed, or whatever variables that you have that help explain your deer activity, that those numbers are as close to this range, or preferably they are within this range in order for this model to be accurate. As soon as your numbers start going outside of that range, your model is going to be less and less accurate. So make sure that you pay attention to the range. If there is a severe drop in temperature, I would not rely on this model in order to forecast deer activity, or if there is a severe change in wind speed or what have you, I would not rely on this model. So as long as the values are within these ranges that we have here, we should be fine. Even if they're slightly outside of it, just expect to see a little bit of error whenever you are mapping out or forecasting your deer activity. So hopefully this exercise was useful for you, and hopefully you can see how powerful regression analysis can be. Now, there are a number of tools out there that can make this whole process easier, but by getting into the numbers yourself, you can see how this whole process happens. In our upcoming tutorials, we're going to be cleaning up this formula and graphing out data points. I think we did enough for today, so thank you so much for watching, and I hope you enjoy your time on Trailcam Data this season.